I think we can start. Welcome everyone to session 7, transportation planning and policy. Before starting, I apologize for my voice. I got COVID and the symptoms started yesterday. In this session, we have 5 presentations, each of them around 20 to 18 to 24 minutes. We'll start with the first presentation. Our first presenter is Dr. Yu. Dr. Yu is an assistant professor in the Department of Civil Engineering at McGill University. His research interests are human AI interactions in future mobility systems. Before joining McGill, Dr. Yu worked as a senior engineer at AECOM and collaborated with MIT and UC Irvine. Dr. Yu is a registered professional engineer and a licensed professional transportation planner. So in his first presentation, he has 2 presentations today. In his first presentation, he's going to present interpretable state space model of urban dynamics for human machine collaborative transport planning. Dr. Yu, feel free to start your presentation.
Great, thanks, Fatima. Let me just really quickly share my screen okay. So how's my screen? Can you see it?
Yeah, we can see it.
Okay. Cool. Hello everyone. So my name is Jumbo, and my first presentation is about a interpretable state-space model. This is mostly will be intended for using by human or transportation planners as well as the machines. Hopefully, they can eventually work collaboratively. Because with rapid development of AI, it is increasingly likely that AI will play a critical role in the future long-range transportation planning. However, the robust and rigorous models that planning agency can use to explain decisions to the public, reconcile conflicting interests, and justify their actions. Over the past 3 years, Professor Michael Hyland and I have been developing such a model, a modeling system that can be used for both humans and AI independently or in collaboration. We refer to this model as the interpretable state-space model, or ISSM, for human-machine collaborative transportation planning. So in this presentation, I will first introduce the context and motivation, and then I will present the model formulation of the proposed ISSM and its desirable properties for usability, following which is a case study of San Diego County, California, and lastly, I will discuss the potential directions for future research and development. The transportation planning can be seen as a feedback control problem involving a planning agency and an urban system. The agency can implement policies, invest in projects, allocate funds for asset management, and reach out to the public. The urban systems provides performance feedback, which the agency uses along with the guideline and the heuristics to make a decision for the next time step. In this figure, we illustrate a typical planning process with 3 major phases, generally sequential, but allowing for iterations. The first phase is the sketch planning phase, or strategic planning phase. Usually, this phase has a broad scope with low resolution, integrating transportation and land use. And the second phase is the regional, commonly known as the regional transportation planning. This phase uses models like the 4-step model or activity-based travel demand model to study low-resolution projects with fixed land use. And the third phase is usually called project programming or improvement program. This phase focuses on the detailed local scope, determining specific project configurations and their implementation timings. So as you can see, the timing of the project won't be considered until the second or even the third phase, but those phases will not comprehensively consider interaction between transportation and the broader natural and built environment. It is apparent that such timing factors are important For example, in terms of the system performance in, say, 2060, whether a set of sustainable mobility projects is implemented in the year 2025 or 2059 matters. Only considering the equilibrium condition in 2060 cannot capture the importance of the project coordination and their implementation timings. So traditional processes, planning processes, often overlook the sequential effects and the interactions with the broader environment until later phases, using a critical implementation timing factor. So we are proposing a dynamic model. However, being a dynamic model is not enough. We must make sure that the model has a unique solution, avoiding confusion from multiple possible outcomes. It should also possess Markovian properties for capturing the response to the disruptive events and for enabling the application of AI techniques such as reinforcement learning to determine the optimal investment strategies. So our framework comprises several components, each represented by state variables, such as households, employment, infrastructure, and land use. The system's involvement is described by differential equations governed by a vector function m, and each state variable corresponds to a tangible, concrete quantity in an urban system. The tangible variables and the hydraulic interpretation make the model interpretable. Furthermore, we can adjust the model resolution by splitting or combining related state variables so that we can, the model has the ability to adjust the resolution. So we can show that the transition rate, regardless how high the order is, can always convert it into this form with first order differential equations. Following the hydraulic analogy, we can split the function m into two major components. The component on the left represents the increase rate of the corresponding state variable, which is always in the form of base rate variable beta, multiplied by a set of state variables scaled by a reference value and the elasticity parameters. This form is then further multiplied by a set of action variables for their scaled version. The component on the right represents the decrease of the state variable, which is the first divided by a non-zero delay, representing the average delay at the present resolution for the corresponding variable. This delay variable is then determined in the form of a base rate, also in the form of base rate variable beta multiply a set of scaled state variables and action variables. So one immediate benefit of this form is that the immediate transition rate from t to t plus dt is always monotonic. We capture this nonlinear effect of the state and action variables through the interaction of those fundamental monotonic variables. Furthermore, we can show that this form preserves the Markovian properties. That is, we only need the information about the system state at time t to infer the system state at t plus dt. This way, we can study immediate response of the system to the unexpected events. We can further show that the proposed modeling form can also provide uniquely exist solution. But because of time limit, I won't talk too much about it. But you can check out our paper right now is under review, and I will show that paper later after the talk. To clarify the importance of the resolution existence and uniqueness, suppose we have an extremely simple one-dimensional urban system dynamic model. As you can see, this particular form, only one-dimensional, has at least one solution, which is in this form. But we'll quickly realize that, for example, if the solution is in this form, it is also satisfy the corresponding differential equation. In fact, any function, as long as we have a real number a, positive real number a, this functions always satisfy the ordinary differential equation at the beginning. So you can see that even just a simple urban dynamic model might not necessarily have solution, and it's also possible to have infinite number of solutions. So in addition to the important property of existence and uniqueness, we can also show that the proposed model has a desirable property such as continuous dependent on initial state and parameter values. And another important property is this solution stability, meaning if I change or the user changes a little bit of the initial condition or the parameter values, the solution of the systems is also only change a little bit, which is a very important property for planners to use. So the proposed modeling framework also facilitates the estimation and calibration, because if you take the log on both sides of the equation, or basically the function m, vector function m, we can use the linear regression techniques to estimate the model parameters. And then, so lastly, we can define a reward function R that can evaluate the system state based on the multiple weighted objectives at each time step. We can also calculate the reward function R with or without discounting factor. The reward information is important for later when we use the proposed interpretable state space model, or ISSM, for training reinforcement learning agents. We apply this approach to the San Diego region of Southern California. So in 2020, it has a population of around 3.3 million people. The region is renowned for its beautiful coastline, vibrant cultural scenes, and the thriving technology industries. However, San Diego County or San Diego region faces numerous challenges, including rising housing costs, traffic congestion, environmental concerns. So balancing growth with sustainability remains a key issue for the Metropolitan Planning Organization, which is also known as the San Diego Association of Governments, or SANDAG. So here is the model of used for this particular case study, which has three major components: infrastructure, social economic conditions, and the land use. So we did a calibration using the data from 2020, 2022 to 2050, using the baseline condition defined or projected by SANDAG, and we find the model can capture the expected future conditions and the baseline conditions by SANDAG pretty well. And then we use the historical data from 2005 to 2022 for validation. Those data are mostly documented in the SANDAG performance monitoring reports. And you can see that it also captures generally well, except that as expected, when we set the initial condition to be 2005, the model itself didn't really realize the pandemic, so it only becomes off around 2020. So it's actually important to highlight the importance of quickly updating or timely update the urban dynamics function or urban dynamics models in a timely manner. So here is a very simplified model. The parameters, I hide these parameters behind, but at least it captures the overall idea of the model simulation. So we can see that during the simulation, the model allows me, the user, to adjust the corresponding decision variables, such as infrastructure, capital investment, the congestion impact fees, and the land use pricing fees. But of course, the idea here is not to let user or urban planners to adjust it when they're using it manually. The idea is we hope we can train an AI agent or a reinforcement learning agent to try this many, many times so that the AI can figure out the optimal timing and the adjustment of those decision variables. So what we did is that we created a reinforcement learning agent and to try to use the urban dynamics models or ISS model to train the reinforcement learning agent. And the result really shows our initial suspicion that the coordination among different decision variables, even at the strategic planning level, is actually very important. We can see that the performance with and without the project coordination or project and policy coordination actually do make a difference in terms of the overall reward of the urban system. And then within the coordination, we also see that different coordination strategies actually will also impact the overall system performance. So we further, because the planning agencies sometimes want to know the impact of different decision weights on different objectives, on their impacts on the final decision making or the urban system performance. So we did a sensitivity analysis test to test different decision weights, and we do notice that it provides a reasonable sensitivity to the variation of decision weights. So as a conclusion, our model, it is we did believe that we proposed the first state-space or Markovian decision process model for land use transportation interaction, at least for the sketch planning phase, even though we do think our model has certain level of flexibility. And our model is explainable, and all the variables are tangible quantity that are understandable by human planners. And the model has some very important desirable properties that to allow the planners to use with confidence. And we do believe that this particular model will facilitate the development of reinforcement learning agents, and hence the potential future of human AI collaborative transportation planning. And I appreciate your listening. And if you want, you can contact me or Professor Michael Highland and check our current preprint of the paper, which is currently under review. And at the same time, I also want to mention that I'm currently hiring master and PhD students. So if you're interested, you can reach out to me as well. And thank you for your listening.
Thank you so much, Jiangbo, for the great presentation. Is there any questions? So I cannot see if there is any question. Can you raise hand? Maybe there isn't any. So I have one general question. Great model. I don't have any question about the model. My only question is about the application of the study, and what is the a single policy implication that you can have as the conclusion of this study?
One of the interesting finding we find, actually pretty robust, even though I think it's a little bit not necessarily controversial, but it's challenging to implement, is that it's actually very effective for the planning agencies to impose a very high congestion pricing at the beginning. At the same time, invest heavily in infrastructure. This way, the new capacity will be mostly used for growing the new households and employment, instead of serving the induced demand of the existing business and the households. And once the households and employment catch up to, and it basically means the transportation system is becoming congested again, this is the moment that we can actually pull out the high congestion pricing. So this way of like iteratively, coordinatively in this particular oscillation pattern is actually very effective in terms of boosting the growth, and we also at the same time reduce the induced demand. So this is kind of the biggest lesson we learned. We actually mentioned it in the paper, but we do understand that allowing the people who are in charge of the congestion pricing, and then allowing the people, and then the agencies that are in charge of constructing the highways and transits are not the same people. So it's very hard to let them coordinate. But this is the major finding from our paper, by assuming that they are allowed to coordinate. But yeah, thanks. This is an awesome question. Thank you for asking.
Thank you so much for sharing the great observation. Yeah, that was so interesting. Is there any other question from Django? Don't be shy, ask questions. So So if there isn't any other question, we will jump to the second presentation, again by Jianghu, on-demand mobility services for urban resilience. So please feel free to share your screen. It's shared already, so share the presentation.
Yeah. Sorry, let me just put that presentation.
Thank you.
Can you see now?
Yes.
Okay, great. Okay, so me again. Thank you, everyone. So this particular talk is shorter, promise. And this talk is mostly about the using on-demand mobility services for improving the urban resilience. This is mostly a literature review, but we did through the literature review we draw some insights and potential and suggest some future research directions. This is through a collaboration with my students, Matthew Thorpe at McGill University. So we know that transportation systems are facing various challenges ranging from safety and emission to the insufficient and inequitable services to the various disasters and hazards. So one natural question, because of the emerging trend of mobility on demand services or MOD, I think it is important to design the services in a way that at least not make the system worse. But even better, will be if we can actually use more services to address some of those issues. So, so its natural question is whether we can use more services for improving community resilience. Some immediate ideas can be like using the more services for evacuation and delivering essential food or medicines and water. And then during disasters, we can use more services, like mobility on demand services for like disaster monitoring and detection and even essential supply delivery. And even the vehicles are equipped with additional technologies like electrification, for example. We can actually use the vehicles for transferring energy temporarily for satisfying the unmet demand of the energy. We can also like transport repair crews using the on-demand mobility services so that we can directly send them from their homes instead of offices directly to the damaged locations for repairing the infrastructure and equipment. So because of this interest, we decided to conduct a literature review. So the method is nothing particularly new. It's just a standard method. We pulled paper from Scopus, Web of Science, Google Scholar, and we used the 4 groups of keywords: service model, and transportation tools and different modes of transportation of the mobility on demand services, and then their particular purposes and then the disasters scenarios. And then we did a initial screening and then a more detailed screening. So we eventually find about 55 highly relevant papers. And then what do we find? The initial word map shows that, not surprisingly, there's these keywords such as system, disaster, communication, management network, ad hoc information. Those are the keywords from those literature. At the same time, we did notice the increasing interest of this topic, and they are actually also highly influenced by major events or the news. For example, it seems like there's a major increase from 2005. It's very likely to be triggered by Hurricane Katrina in New Orleans. And later on, there's a decline, but later on it's increased again, probably because of the Fukushima nuclear meltdown caused by an earthquake. And later on, it calms down a little bit again until Hurricane Sandy in New York, or the east coast of the United States, and then that's lasted a few years, and then it's reduced again, and then until recently from 2020, there is a major surge of this type of papers, very likely to be caused by the pandemics and also the increasing concern on climate change. So if we pull the data keywords of those data, we see that those major, in this map, the bigger the node means that the keywords is more likely to occur. And then at the same time, if the two keywords are connected, closer to each other, that means they're more likely that the same keyword appears in the same article. So but it still is very challenging to see. So we run a little bit of the unsupervised learning, and we find this kind of 5 major categories of papers. So we have the papers that mainly discussing about how to improve the resilience of the mod services itself. And we have the papers that are mainly discussing about the technologies and the algorithms that enable or augmenting the mobility on demand services. And we have the papers that are proposing novel usage of mod services. And we have papers that are emphasizing on learning from the past, like what mobility services have been used for improving the community and the infrastructure resilience in the past, and how effective they are. And another major topic seems related to the human roles and the human machine teaming. But this part, we notice that those discussions are mostly in the area of in the discussion sections or the conclusion sections. So those are mostly for projecting the future research steps. So what I did for the rest of the talk, I'm going to talk about the first 4 main themes or topics: the resilient mod services, the impact of an impact evaluation or the empirical evaluation, and then the third is the novel mod usage, and then the fourth is enabling and augmenting technologies, and then I leave the 3 major research gaps or the future directions to the last section of my talk. For the first theme, the resilient mod services, we noticed that there are 2 major levels of the concerns. One is the planning level. So there are researchers who have been discussing about the optimal location of the park and ride facilities for disaster, for better responding to the disruptive events. And we have people studied predicting the behavioral response to disasters, and also the collaborative governance of services. And at the operation level, we have the study on how to build a mod platform to be robust to fluctuation of demand, and how to integrate those mobility services with public transport to improve the resilience of overall mobility systems. And we have the study of using mod or on-demand transit during pandemics, and as well as how to improve the mod platform to better handle or address the cyber attacks. And then in theme 2, we have people studied the ride-hailing services, how they have been used for improving the unplanned rail disruptions of transit services, and how using bike sharing systems have been used for serve essential travel needs during pandemics. And in theme 3, we have people mostly suggesting the novel use of mod. I mean, now that because they're already proposed, they're not new anymore. But back then, there are new concepts like using ride sourcing services for hurricane evacuation, using the mod services, especially when they're electric vehicles with the vehicle-to-grid technologies. They can be used for transferring energies, and then they can be used for delivery essential supplies and transport repair crews, as I already mentioned a little bit. And then vehicles actually can also be used as a prop vehicle for disaster detection and monitoring. For theme 4, there are 4 major types of technologies that have been recurring in different papers. One is the the potential use of automation, artificial intelligence, and robotics to further enhance the mod services for resilience improvement. And we have, because one of the major aspect of it is during disasters, we don't want to risk human drivers' lives. That's definitely a benefit of using the autonomous mod services. At the same time, because it's automatic, so we don't have to wait for human drivers to respond. So it could be increase the response speed. At the same time, and if the disasters happen at midnight, it's especially beneficial potentially. And the electrification, it's one of the major synergistic technology is the vehicle-to-grid technologies, especially when the urban area has the corresponding discharging facilities. And advanced communication is another important aspect where if we had the ad hoc, use the mod services vehicles can serve as the potential ad hoc communication networks, because it's likely that during the earthquake or hurricane, the power network and communication network will be down. So in that case, the vehicles can serve as a node for temporary setting up communication networks. And another aspect is the virtual and mixed reality that people have been used for collecting public opinions and expertise in disastrous events for mod service planning. So as I mentioned, there are three major research gaps from those papers. One is the integration of technologies in different modes of mods services, and then the integration of different information sources. And another aspect is how to use both the human intelligence and the machine capabilities, especially the autonomous vehicles, to form a team together to serve a better, improve the community resilience. Because if you think about it, even for autonomous vehicles, it's unlikely that they can deliver once they arrive at the destination, it's unlikely that they can deliver the food and medicines and waters directly to the doorsteps. Because probably we still need social workers. At the same time, the respondents of the disaster respondents are still likely to be humans in the near future. So in that case, it's important to develop a decision support tool for them to use instead of completely based on their judgment or the emergency response plans. And another aspect, which is linked to my first talk, is the incorporation of the overall long-term plan, long-term transportation planning. And then I know that in US at least, the metropolitan planning organizations already consider some aspect of improving the community resilience in the long-term plan, but I haven't seen any MPOs that are explicitly considering using mod services for this and how to foster that capability. So I think that's could be an interesting aspect for future research as well. But the eventual goal, of course, is to enhance use through planning and better operation. We can improve the community resilience through mod services along with other technologies and models, service models. So that's it. And here, if you're interested, you can check out our preprint, and or you can reach out to me to further discussion. And again, I'm hiring master and PhD students, so please let me know if you're interested. And thanks for listening.
Thank you again, Jiangbu. So questions for Jiangbu? Any questions? You can also type your questions in the chat box if you have any. I just have one question about the integration of different mobility on demand services in terms of the framework. So do you think that it is possible that people change modes more than once? For example, use a scooter and then use a van to connect to transit and then use transit? Or the integration is more useful in cases where we would like to, use scooter and bikes for short distances and vans and other cars for longer distances.
Yeah, I think it's certainly that you mentioned a great point. That is, different modes of mod services have their strengths. So if the disasters or disruptive events is in certain nature that is only the scooters or the bicycles or the regular vehicles are useful, then we should use that. But if it is we need to like a long distance, say long distance evacuation because of the wildfire, and in that case, scooters is probably not very helpful. And then also the transit, it's only with usually the subways is within the city. But maybe bus we can temporarily reroute and then let the bus to for evacuation purposes when it's on-demand buses or shuttles. Um, but that's actually exactly like highlighting the need of integrating all those services, so that when we're facing different types of disasters and disruptive events, we can know exactly the optimal integration of those mobility services for adaptability improvement of the communities. Yeah, but yeah, that's a wonderful question.
Yeah, thank you so much. Thank you for your great presentation. Beautiful visualizations. I like your visualizations.
Yeah,
thank you so much. So we will go to our third presentation. Our third presenter is Sajjad Wusuqinia. He has a master's degree in transportation engineering from Sharif University of Technology in Iran. His master's thesis was on timetable synchronization and optimization in urban railway networks, which I think is today's presentation is about that topic. After his master's, he started a PhD position at Michigan State University under supervision of Dr. Mernaz Ghamami. Sajjad will present a study on timetable synchronization optimization for urban rail transit network today. So Sajjad, please feel free to share your screen and start your presentation.
Thank you, Dr. Kahmousavi. Hello, everyone. Just a second, please.
We can see your presentation, but not in the in the presentation mode.
The title of the study that I'm going to present today is Timetable Synchronization Optimization for Urban Transit Network. And we have done this study at Sharif University in Iran. So first, I'm going to go through the introduction, literature review, and the contribution of the study. Then we have the mathematical model, hypothetical example, and the genetic algorithm we use in this study. And then we have our case study and conclusion. So as you know, rail transport widely plays a significant role in reducing street congestion and environmental pollution, and it can be beneficial in terms of decreasing investment in the construction of public parking spaces, fuel consumption, environmental sustainability, and such things. And the timetable includes various elements such as departure and arrival times at each station, the time interval between consecutive trains, and whether trains stop or proceed without stopping at different stations. And the stop skipping strategy, especially at those stations with low demand, can be highly effective. And also the absence of a schedule coordination between different lines makes passenger transfer more challenging and time consuming, leading to passenger dissatisfaction. So for the literature review here, we have the three main papers that we use in our study. We use the most in our study. The first one is Shang. He proposed a time-dependent passenger demand-driven timetable synchronization optimization to minimize the total travel time for passengers, and they use the genetic algorithm to solve larger-scale problems. The second one is Wang. He proposed a mixed integer programming model considering train capacity and time-dependent demand to minimize total waiting time and also number of passengers who fail to transfer. And the last one is Motawallian. She proposed a mixed integer programming model to create a synchronized and optimized timetable for two lines of a railway network. And also they use the genetic algorithm for just 2 lines of a railway. So the main contribution of this study is considering synchronization and stop-skipping strategies simultaneously, including both transfer and non-transfer passengers in our model, considering train capacity constraints. And also this proposed model is not restricted to a specific number of lines within the network. So here we have our model assumptions. The first one is the dwell time of each train, as each station is a fixed and predetermined number. At the transfer station, the amount of time passengers must walk to get to their next line is predetermined. When a train doesn't stop at the station, the next train is required to stop at that station. And the last one is all trains must stop at the first, the last, and the transfer stations in the line. So the objective function of this study is the minimization of 4 different parts, T1, T2, T3, T4. T1 is the waiting time of all passengers at the origin station. T2 is the transfer waiting time at the transfer stations. T3 is in vehicle time. And T4 is the number of passengers successfully reaching their destination. And because we want to make sure that we want to maximize the number of passengers reaching their destination in our study horizon, T4 shows up with negative sign here. And also we have 4 different coefficients, and they will be determined through the sensitivity analysis. Here we have our mathematical model. The first 4 parts, they are the different parts of the objective function. They calculate the total waiting time at the origin station, total waiting time at the transfer stations, total in vehicle time for all passengers, and also number of passengers reaching their destination. Then we have our different constraints. We have dwell time at each station. We have running time between 2 consecutive stations, minimum and maximum headway, the constraint about the study horizon. And in number 11 is for the constraints that we mentioned, 2 consecutive trains must not skip a station. And number 11 calculates the arrival time of passengers at the origin of their subtrips. Then number 13 and 14 specify the train that passengers board during their subtrips. In number 15 and 16, we calculate the waiting time and in-vehicle time for passengers. Number 17 and 18 calculates the number of passengers getting off the train, and number 19 and 20 calculates the number of passengers getting on the train. And finally, we have the train capacity constraint. So to evaluate the performance of our model, first we created a hypothetical example. We can see in figure 1, we have 3 different lines with 3 or 5 stations in each line, and we generated a random demand for this OD pairs. And in table 1, we have the calibration of the objective function coefficient. Alpha 1 and alpha 2 is the coefficient of waiting time at the origin station and waiting time at the transfer stations. And alpha 3 is the coefficient of in-vehicle time for passengers. And as you know, the waiting time is a more distressing activities for passengers, and they perceive it more than the actual waiting time. So based on reviewing the literature, we decided to set the coefficient of waiting time 2 times of the coefficient of in-vehicle time in our model. And for alpha 4, we did a sensitivity analysis. You can see in table 2. We have different values for alpha 4. We have 30, 40, 50, 60, and 70. And actually, we solved the example for each value of alpha 4 with a CPLX solver in GAN. And because we want to make sure that we transfer passengers as much as we can. So as you take a look at the T4, it goes up by different values. And after alpha 4 is 60, it remains the same. So we had a comparison between alpha 4, 50 and 60 to see which one works better. And if we set alpha 4 to 60, the number of passengers improved by 0.9%, but the first three parts get worse significantly compared to alpha 450. You can see by 7%, by 40%, and 1.3%. So we decided to set alpha 4 to 50 to transfer passengers in the study horizon as much as we can, but in a way that we don't increase the other part too much. So here we defined two different scenarios to kind of evaluate our different strategy. We have our purpose scenario that we consider both stop skipping and synchronization. And in the first scenario, the stop skipping strategy is removed and it requires all trains to make a stop at all stations. And in the second scenario, the timetable synchronization removed and it means that the subsequent trains depart with a specified headway. And also the different lines in the network are independent of each other. So you can see the result of solving different scenarios in table 3. And if you sum up the passengers waiting time at the origin station and the passengers transfer waiting time at the transfer station, and also the passengers in vehicle time and divide it by the number of passengers reaching their destination successfully, we get the average travel time for each passenger that you can see in the last row of table 3. And for our proposed model, it is 10.81. And for the first scenario, it is 11.06, which is 2.3% more than the proposed model. And for the second scenario, it is 11.23, which is 3.9% more than the proposed model. And it shows that both our scenarios and the strategies are effective, and we need to have stop skipping and synchronization in our model. So as you know, for solving larger scale problems, it's not possible to solve it by exact solvers such as duplex solver in GAMS because it takes a long time and actually it's not possible. So we need to have a heuristic algorithm to solve larger scale problems, and based on reviewing the literature, most of the papers using genetic algorithm in this case. So here we use the genetic algorithm, and for each chromosome in this algorithm, it includes the departure time of each train from the first station and also the binary variable that shows a stop or no stop at each station. And that's because if we have these two variables, we have all the variables we need for our timetable. And then we have our fitness function. It includes our objective function plus a penalty term. And the penalty term here is for considering the train capacity constraint. And if the number of passengers in the train exceeds the capacity of the train, so it will add a penalty term to the objective function. In figure 2 here, we have an example for the chromosome we have in our study. So here we have the genetic algorithm flowchart. For the input section, we have our network data, we have the travel demand, we have different parameters such as the population size, the probability of each operators, and such things. And for the initialization, we generate n random solution or n random chromosome, and we set this population as a parent set. Then we need to calculate the fitness function for this parent set. And then we need to check if the termination condition is met or not. And if the termination condition is not met, so we need to produce a new population as a child set. And we have 3 different operators here for our reproduction. We have elitism, we have crossover, and mutation. And by elitism, we mean we keep the best answers of each generation and we transfer them to the next generation without any changes. So in this way, we make sure that the best answers of each generation is better than or equal to the previous one. And so then we have our new population, which is the child set, and we have to set it as a new parent set and do the same things again. We have to calculate the fitness function, and then we have to check the termination condition and so on. So we did a sensitivity analysis here to determine the probability of each operator in our genetic algorithm. So we keep the elitism percentage to 10% here. and we just change the crossover and mutation percent because by elitism, we just want to make sure that the best answers are better than or equal to the previous generation. And if we increase this percent, it takes a longer time to get to the result and best answer. So here, for each case, we solved our hypothetical example with genetic algorithm 5 times, and finally we calculated the average value of the objective function we got and the average value of the number of generations. And we concluded that the best combination is 60% crossover, 30% mutation, and 10% elitism. And then we solved our hypothetical example with genetic algorithm, and you can see in figure 4, it gets to the best answer in a short time, which is less than 100 generation. And in table 5, we have a comparison of the results of solving the example with a simplex solver in GAMS and the genetic algorithm. And they're exactly the same, but just the genetic algorithm solved the example in 178 seconds, which is significantly lower than the time that simplex solver takes to solve. So here we have our case study. We consider 3 lines of the Tehran railway network, and we used for the demand we used the typical weekdays, and in table 6 we have different parameters of our genetic algorithm for the case study. We chose 2 peak hours from 5 to 7 p.m. And also we have the number of trains and the dwell time, transfer waiting time, the minimum and maximum headway, and the number of population for our genetic algorithm. So here again, we have 2 different scenarios. Again, our proposed model considers stop skipping and synchronization. And in the first scenario, the stop skipping strategy is removed and all trains must stop at all stations. And in the second scenario, both strategy remove the stop skipping and timetable synchronization are removed, which is the current state in the Tehran railway network. And here we have, in table 7, we have the result of solving the case study with genetic algorithm. And again, if you sum up the waiting time at the origin station and waiting time at the transfer station and also the passengers in vehicle time, and we divide it by the number of passengers reaching their destination, we get to the average travel time for each passenger, which is shown in last row. And for the proposed scenario, which it is 25.19. And for the second scenario, for the first scenario, it's 26.02. And for the second scenario, it's 26.25. And here for the conclusion, our proposed model reduced the total travel time for each passenger by an average of 4% during peak hours on 3 lines of Tehran railway network compared to the current state. And it also resulted in 26.5% reduction in total passengers transfer waiting time, and also 3.6% reduction in total passengers in vehicle time. And it also increases the number of passengers reaching their destination by 0.7%. And also utilizing a genetic algorithm for model solution has proven to be an effective approach in handling large scale problems within a shorter time frame. And for future research, we recommend exploring alternative heuristic algorithms to solve the model more efficiently, or we can include additional variables such as the number of trains, the dwelling time, and running time between stations. And that's it. Thank you for your time.
Thank you so much for your presentation, Sajjad. So we have one question in the chat box. Martin Schmidt is asking how you determine which stops to skip.
Actually, we determines the those stops with low demand in a way that our total objective function reduce significantly. And yeah, that's it.
Okay, so does this answer your question, Dr. Schmidt?
Sorry, can you come again?
Oh, nothing. I was just asking him if you answered, and okay. So my next question is about your objective function. You had different weights in your objective function, especially the fourth term, which was number of something, is not comparable to the first three terms, which were times, weight times. How did you set those weights, and did you do any sensitivity analysis?
Actually, because we are using a stop skipping strategy, so it may result in skipping some passengers. And actually, we put the force part in the objective function because we just wanted to make sure that using a stop skipping strategy may not result in passenger dissatisfaction. So, and that's because the scale of the coefficient is totally different with the three first part, which was 1 or 2, and for the last part is something around 40, 50, or 60.
Let's see. So is there any other question for Sajjad? No? We have time for more questions. Okay, so with this, we'll go to our fourth presentation with our third presenter, Dr. Jason Hawkins. Dr. Jason Hawkins is an assistant professor at the University of Nebraska Lincoln. He's going to start a position at the University of Calgary this fall as an assistant professor. He's one of the organizers of this great conference, and his main research interests are energy and GHG emissions of infrastructure, travel demand forecasting, and econometrics modeling, especially with applications on large data sets. So Jason is not a co-host yet. Please, Donya, make him a co-host.
Yep, I am now.
Okay, great.
Great, thank you. So let me just share my screen. So thank you, Femi. This is some work that I did with my colleague Osman Ahmed at the University of Toronto, who's also starting a new position soon at the University of Tennessee. So this is work that we did jointly, I believe, Osman this year, but he's in Pakistan and it's very late, so I'm going to present on behalf of us today. So a little bit different. We're looking at land price modeling here and the effect of transportation on land prices. And the focus is partially on this question of how do you do cross-validation with spatial data, and what are some of the challenges that arise from that. But then we also use an application in Toronto and in Islamabad in Pakistan. So kind of also have kind of a nice comparison between those two regions. So a bit of background. Data-driven machine learning approaches are increasingly common in transportation engineering, also regional science, which is sort of the area that we're kind of working in here. And so given the nature of these sorts of regional problems, how do we ensure accurate inference? So specifically the question that we're looking at here is, how does cross-validation, whether it's aspatial or spatial, and I'll describe what I mean by that, affect model results? And then, as I said, the empirical application is residential property prices in Islamabad and Rawalpindi, Pakistan, and in Toronto, Canada. So this is kind of a spatial representation for you. So on the top, you can see a random cross-validation, and then in the bottom, you have spatial. So the idea here is that if we look at this by color, you have kind of a random assortment of different shapes and colors, but both your training and your test data set contain a mix of each type of property here. So the methods of analysis, we used random forest and then XGBoost in this model. And then, as I said, we look at this cross-validation method, comparing a random sample and then a spatial sample. And then we look at the empirical results using Shapley additive explanations. Just realizing I might have an older version of this presentation that is just Pakistan, but that's okay. It still gives the basic idea. In the final paper we looked at Toronto, but I forgot to update this presentation, it seems. So the area that we're looking at is the Islamabad area in northern Punjab. It's about 3.1 million people. And then in the data set that we're using, there's about 19,417 property transactions, and kind of a split between the two major cities in the area. So the empirical application, we have some property variables, but we also have transportation variables. So distance to a bus stop, distance to highways, roads, freeways, interchanges, railway stations, how do these different variables, which have been found in the literature to affect property prices, affect prices in this region. And then bus stops here are divided between two types. You have metro bus stops, which are sort of high frequency, or well, sort of stricter separation, kind of a higher quality of service, and then regular bus stops. And then we have the variable of, is there a highway within 1 kilometer or 2 kilometers, and then sort of similar for primary and secondary roads. The region has 2 airports, the old and the new airport, and so we look at the distance to those. And then we also look at the distance to several markets as kind of proxies for sort of the downtown, sort of central business district of the major cities. So let me just show you what this looks like. So if you think about aspatial cross-validation, you get something that looks like this. So the 2 different colors are whether it's the training or the analysis set or the test or assessment. What you can see here is it's just sort of a random sort of scattering of points. If we look at this spatial cross-validation on the other side here, you can see that we are training the model on one particular region and then testing it or validating it on a different region. And the issue that we're looking at here really kind of arises from an underlying assumption of cross-validation, which is that you're taking random independent samples. When you're dealing with spatial data, as we are here, these are not random independent samples. You can sort of think of if you are training a model on your house's property price and you're trying to predict the property price of your neighbor, those are probably much more similar dwellings than if you train a model on your house price and then you try to predict the housing price on the other side of the city. They're, different real estate markets. The houses probably look, a little bit different. And so we can sort of think of, well, this is probably an easier problem. You train on this blue data set, this red data set, and predicting the blue data is probably a little bit easier than in this case where there's sort of this spatial separation between the two. And we'll see that kind of hypothesis or intuition is sort of borne out in the results. So just sort of some basic statistics that we can look at. you can look at an R squared or an RMSE, the root mean squared error. And this has been looked at in several other studies where similar results have been found. So you can see on the right-hand side here, we have the aspatial model, and it's fairly consistently predicting a high R squared and a low RMSE, so a very good fit. If you compare that to the spatial model, when we train and test on different areas of the Islamabad area, we get a much lower R squared and a much higher RMSE, sort of suggesting that that this aspatial model is sort of over predicting its ability to do out of sample prediction, because again, in some sense, it's not really doing out of sample prediction. It's just predicting on your neighbor's house, which is it's sort of functionally the same sample. And so we can look at some of these results then and see, not surprisingly, that the area of the dwelling has a significant effect on the results. The distance to Islamabad downtown has a significant result in the aspatial model. Distance to railway stations also has a significant effect. But just to sort of highlight here that, yes, we get that in both models, area tends to be an important variable. If you have a bigger house, you pay more for that. But when we estimate these two different models, you can see that there's some differences here in sort of the importance of different variables. And so if you estimate this with the aspatial version, you're going to come up with different inferences than you would if you were using the spatial cross-validation method. So sort of touching on a little bit of what I've talked about here. As I said, floor area comes out as the most important. Proximity to highways is sort of least important in predicting property sales prices. We get some nonlinear effects, so longer tails on one side of that SHAP diagram than the other. Accessibility to transportation infrastructure does affect prices in Islamabad, and I'll say, even though I don't have it in the presentation, we do get similar results in Toronto. Some conclusions and future work on this is we confirm some of the work which has been done in ecology and a few other fields looking at comparisons between spatial and aspatial cross-validation, that by ignoring this spatial dimension, it leads to significant bias and potentially inferential errors. Blocking in the spatial structure data sort of restricts the predictor space, though, meaning that you're potentially doing extrapolation. So that, maybe you've trained the model in a very high income area and you're testing it on a low income area. You sort of would expect lower prediction error, but it also means that you're very much doing sort of out of sample prediction. We could do there's some other sort of strategies on sort of blocking the data in predictor space and not just sort of spatially. But ultimately, one of the challenges that we sort of identified in this work is that it can be challenging to incorporate sort of the flexibility of machine learning with typical spatial econometric models. So a model like the spatial lag or spatial error or spatial Durbin model that are very popular in spatial econometrics and used a fair bit in transportation analysis as well. And the reason for that is that those all rely on a spatial weight matrix. And so given that a lot of these machine learning methods aren't likelihood-based, you can't necessarily sort of directly apply that. And in fact, we've reviewed a few papers that have incorrectly done this. by including a spatial weight matrix and say a random forest model, and there's sort of reasons for why that's not sort of a feasible option. And so one of the directions that we're pursuing, and I actually am estimating some models with this very moment, is using what's called Bayesian additive regression trees, or BART, which is sort of a flexible model formulation, but it has a likelihood basis because it's a sort of Bayesian statistical model, which means that you can incorporate a likelihood into it that includes a spatial lag effect, while still maintaining the flexibility of sort of machine learning. So I'm happy to take any questions that you might have on this work. And I believe Usman is also here if there's questions for him.
Thank you so much, Jason, for your presentation. Is there any question for Jason or Usman? So we don't have any questions. So thank you so much, Jason, for the great work and great presentation and organizing this conference, being one of the co-organizers. We will go to our last presenter, Kentaro Mori. Kentaro is a PhD student at UT Austin, working with Dr. Kara Kokelman. Prior to joining UT Austin, he did his bachelor's in civil engineering and minoring in mathematics at Lafayette College, and he has a master's in civil engineering from Nagoya University. And his research interests are mostly the impact of forecasting the impact of emerging mobility technologies and devising optimal application strategies and policies for these technologies. So today, Kentaro will present one of his works on comparing different congestion pricing strategies. Kentaro, please feel free to share your screen and start your presentation.
Yeah, thank you for the introduction. Can you see the screen?
We can see your screen, yes.
Okay, great. Yeah, so this work is in collaboration with Doctors Felipe de Souza, Krishnamurti Guberti, Joshua Alt from Argonne National Laboratory, and my advisor at UT Austin, Dr. Kara Kokelman. And in this study, we compare different congestion pricing strategies using a large scale simulation for the city of Austin, Texas. So congestion pricing has been implemented in a few select cities around the world to help meet the mobility needs while reducing congestion without adding more lane miles. Singapore was the first to do so, and they have been evolving their techniques over time. Recently, they launched their ERP 2.0, which replaced area toll gantries in the bottom, showing the bottom left, with satellite-based GPS systems embedded in all vehicles that can process all vehicle fees, including parking. The system is shown at the bottom right. Similarly, London, Stockholm, and Milan also have area or cordon tolls that were inspired by Singapore. And ICT innovations offer opportunities to implement more advanced tolling strategies, even perhaps allowing for tolling lane by lane for all road links in the network. However, there's been limitations in the research in congestion pricing. There are two notable limitations in past research. First is that while congestion pricing affects behavioral responses in many different dimensions, including route, departure choice, departure time, mode, and destination choice, previous research has really consider more than two choice dimensions, which are usually route and departure time choice. Furthermore, we must consider the heterogeneity among travelers, especially in the value of travel time, when looking at individual responses to congestion pricing policies. And while many studies use presumed groupings of values of travel time, this is not sufficient to consider the full effect of such heterogeneity. Luckily, we have a new development in agent-based modeling to tackle both of these limitations. The integrated demand-supply modeling framework of agent-based models allows for the impacts of pricing strategies to be captured across all of the choice dimensions previously mentioned. Furthermore, agents can be defined or synthesized with realistic heterogeneity. So basically, there is a gap in testing the impacts of pricing policies in a large-scale setting in a a consistent way due to limitations that were mentioned in the previous slide. So in this study, we benchmark different congestion pricing policies in the Austin 6-county region using the Polaris agent-based, activity-based simulation framework. So what Polaris does is basically simulates a 24-hour day of activities for a sensitized population and routes them through the network using dynamic traffic assignment. Congestion pricing basically seeks to address the inefficiencies and the negative external costs caused by unregulated travel behavior by bringing the average travel cost of users closer to the actual marginal social costs that they're causing, that they are imposing on it. So first best pricing refers to when a driver entering a road is charged the exact difference between the marginal social cost and the average travel cost. While theoretically this leads to optimum, it is difficult to implement, socially unacceptable, and requires many unrealistic assumptions. And for this reason, many second best pricing strategies have been proposed, and we will examine three in this study. So we'll be comparing to the baseline of no tolls. And the first strategy that we examine is a cordon toll, which is perhaps the simplest form of congestion pricing, which is when a vehicle pays a price when entering a CBD area. And this for Austin, we define this as this area is shown in red, and there are 56 entry points where drivers will be charged. The second congestion pricing strategy we look at is flat rate distance-based pricing, often called the BMT tax. As the name suggests, vehicles are just charged a flat per mile rate for all links to the network. And this has been discussed in the recent years as a possible substitute for gas tax. And finally, the most advanced congestion pricing mechanism we looked at is the daily-based pricing, and it's an approximation of the marginal cost congestion pricing. And it is calculated. It was calculated as using this equation in the study. So basically, for the toll of a link for a certain time period is which is calculated after each iteration of the simulation is defined by the weighted sum of the sum, and the first term is basically based on the delay, which is a difference between the experience and the free flow travel time, and this is extracted from a minute by minute record of the link travel times in the simulation. and this delay is priced at $18 an hour, which we assumed as the average value of travel time. And the other components of the weighted sum includes the link toll used in the previous iteration for the same time period, and the newly calculated link toll for the previous time period for the same link. And the weights that we use 0.6, 0.2, and 0.2. We simulated a typical weekday using Austin's NPO network for the year planning year 2035 with a 25% synthetic population. And we updated the tolls after each simulation until convergence. Now getting into the results, delay-based toll simulation settled at a revenue of $4 million per day, which equates to $1.37 per resident per day, or 51 cents per vehicle trip. And in order to maintain a fair comparison, we priced the distance-based tolls to generate the same amount of revenue, which ended up being 9 cents a mile, which is 4.5 times Texas's gas tax of 2 cents approximately 2 cents a mile, while gas prices are around $3 a gallon these days. Similarly, the current tolls target revenue was set to be comparable, but because it affects a smaller number of trips, it was set proportionally to the number of trips entering the quarter tolls under the baseline scenario, which is 8.6%, and this ended up being a entry fee of $4.83 into the quarter. Looking at the effects of network performance, so both VMT and VHT fell in all cases, which is expected, but often not a result of many studies, mainly because they don't consider all of the dimensions of behavioral responses. So distance-based pricing was the best at reducing the VMT at 3.6%, while VHT reduced most under that scenario at 10.3%. So both delay and distance-based scenarios reduce the total network delay. But when looking at the ratio of the total delay hours to the VHT and the average speed, we see that for distance-based pricing, the reduction in delay actually just comes from the reductions in the distance driven, as people just choose closer destinations for discretionary trips to avoid paying tolls. Current toll had a negligible impacts on the network in terms of VMT, VHT, or reduction in delay. Now I'll share a selection of some the most interesting results that we found. When looking at the departure time shifts, we didn't notice that much for distance and coordinate-based pricing. However, for delay-based tolling, travel actually shifted towards the PM peak of 4 to 6 p.m. instead of having a typical peak shaving effect that we anticipated. And this effect was not seen for the AM peak. And we think this is because the delay reductions allow for more people to realize their preferred activity state start times, and this benefit outweighs the tolls that they're paying. Here's some results focusing specifically on the delay-based strategy. So on the top here, we have the average toll per mile for each hour of the day. And we see that for the AM and PM peaks, the average the toll per mile is 7 cents a mile, which is lower than the 9 cents a mile that's required to generate the same revenue for under distance-based pricing. And on the bottom here, we have the distribution of the toll per mile during the AM and PM peaks, which are, and the spatial patterns are quite similar. Higher tolls in central Austin, while outer links are virtually untolled, even during peak hours. Finally, we analyzed some equity implications in terms of who's going to pay for these tolls. And there is a big difference between delay and distance-based pricing in terms of who pays. So under delay-based pricing, residents of Central Austin incur the highest tolls, but under distance-based pricing, those living in the outer areas pay the most as they drive longer distances. But while those roads are not as congested. So in this study, we simulated coordinate distance-based and delay-based congestion pricing strategies using the Polaris agent-based simulation model for a 25% population of the Austin 2035 region. So delay-based tolls resulted in a revenue of $1.37 per resident per day, or 51 cents per vehicle trip, which nets at $4 million per day. Delay-based tolling improves network efficiency, but distance-based pricing just seems to reduce the distances driven. And this illustrates the importance of incorporating destination choice into the model when studying congestion pricing. And coordinate tolling in the central Austin area had negligible effects on the network performance. And interestingly, delay-based scenario elicited a shift towards the PM peak rather than away from it. And finally, we saw opposite trends in spatial variations of tolls incurred per resident for delay and distance-based strategies, which influences the social acceptability of the policies and who is willing to support it. Yeah, thank you for listening, and please let me know if you have any questions, comments, or suggestions.
Thank you, Kentaro, for the great presentation. We have one question in the chat box now too. Mr. Schmitz has asked if travelers move to different streets around the cordon area, and how do you just check if they change their paths to avoid the pricing zone?
Yeah, so the objective of the cordon toll is to one of the objectives is to reduce the through traffic. So we would expect travelers to select routes that don't go directly through the cordon, and we did see a reduction in the number of vehicles entering the cordon. I don't have the numbers exactly, but yes, yeah, we did see that.
Nice. So the next question is asking by Matt, are there any results on mode shift away from SOVs?
Unfortunately, no. We saw very little change in most shares across all scenarios, and this is likely due to the lack of options in the Austin area. And the results may be different for other cities that have more transit and active transport options.
Yeah, so that is true about the Austin area, that public transport options are limited. So this following up on that question, I have a question as well. So you compared the travelers of from different households, how who pays and who doesn't pay. My question is that it's the main concern about congestion pricing is the equity issue, and if households with lower incomes have have other options and have an alternative option or alternative route, and how much they will lose if we add that congestion pricing policy. So it's kind of a suggestion and a question. If you have done that, if not, suggestion for this paper to report, for different levels of users, different classes of users, for example, for different BOT levels.
Yeah,
You
go ahead.
go ahead. Yeah, I think you got.
Okay.
Yeah, you
Yeah,
can
so I've
report.
done some. Sorry.
You can report how much they lost. That was my question, just to complete. Yeah.
So I've done some preliminary analysis on how different income groups are impacted, and in terms of tolls paid, higher income groups pay more and lower income groups pay less. And but the ratio to their income might be a bit disproportionate. But as far as the responses go, it didn't seem like any income group was, for example, having to take longer routes, or no income group was forced to have a disproportionate response to the policies, which was good. I would like to do a more thorough welfare analysis, which has been difficult with the activity-based model of players having a single log sum to measure the welfare is not something I've been able to do yet. So if you have any suggestions, yeah, that would be great.
So for congestion pricing, we usually, for second-based pricing, we usually check if they are self-funded, revenue neutral for all user systems. So you can, I think there are ways to calculate that and check that, because you have the users, and so we can talk about that after.
Okay, yeah, thank you.
Presentation. So my other question, I think I know the answer. So you, for the first and second congestion pricing strategies, you set the prices. Is that right? You didn't optimize them, or where did you find?
So the delay-based pricing is solely based on the delays that are experienced in the network. And then the distance-based and the coordinate-based pricing, we set a target revenue based on the results of the delay-based pricing, so we can do a fair comparison.
Nice. Yeah. That's nice. Thank you so much.
Thank you.
We have more time. Is there any other question? Yeah, so Matt Stratton said that perhaps a good follow-up scenario, particularly for the distance-based or delay-based scenario, would be to assume that revenue goes into more transit supply. So you can consider it for the next step of your paper.
Yeah, thank you for the suggestion.
Thank you so much for your questions, everyone, and thank you. I would like to thank all the presenters for their great presentations. We are a little bit ahead of the schedule, and we're finishing the session early. If there isn't any question, we can end this session. And I don't know if there is anything else planned after the session. Jason can add.
No, this is the end of the day, but we'll see everyone tomorrow for our next headline speaker in the West, Francisco Camara Pereira from DTU, talking about scalability and generalization of transportation models and simulation with AI, which I think will be a great presentation.
Okay, yeah, we'll hopefully see you all there. Thank you so much, everyone. Take care. Bye.